So hopefully what you've gotten from this lecture is that we've got an E field that's changing its magnitude typically in the A hat X direction. And we've got a H field that's changing its magnitude in the A hat Y direction. And by the right-hand rule, what's happening is a wave is propagating that's perpendicular to both of those. And in this case, that's going to be the A hat Z direction. So a plane wave propagating in space or a conductor or any other material, it's got the E field and the B field associated with it. And as such, it's going to carry a certain amount of energy in the form of electromagnetic radiation. And this energy serves as the basis for the signal captured by a receiving antenna, the warmth you feel when you go and stand in the sun, the heating operation performed by a microwave oven, a whole lot of different things. The amount of energy stored in this wavefront is quantified in a unit called power density, which is just the power per unit area, or it's watts as measured over an area normal to the direction of wave propagation. So if I were to just create some sort of screen that could capture this power, I would say, well, how many watts do I get per meter squared of receiver here? And this relationship, the power contained in this wave, well, it clearly comes from the E and the B field. Well, what's that relationship? It's extremely similar to voltage and current. The power contained in the wave is just equal to the vector cross product of the electric field and the magnetic field. And the units for that, again, are going to be this watt per meter squared. And this here is called the Poynting vector. And this really is a fundamental observation about the nature of electromagnetic phenomenon. An electromagnetic wave, it consists of a coupled electric field and a coupled H field that propagate at right angles to one another. The direction of power transmission is going to be orthogonal to both of them. And this vector is called the Poynting vector. It's named after John Henry Poynting, the guy who developed this theory. And it tells us how much power is being transmitted by this E field and this H field as they propagate through space. Physicists, instead of using P, since that's reserved for power, they tend to use S. We don't use that because that's complex power and, running out of letters, I guess. But physicists will often write Poynting vector as power density S. In general, E and H are both functions of time. And so the Poynting vector is also a function of time. So a lot of times we'll be more interested in the time averaged value of pointing. Just like we are, often we're interested in average power, RMS power, something like that. And so the time averaged power density a lot of times is P average, and that's equal to 1/2 the real portion of the cross product of E and the complex conjugate of H. It's still measured in watts per meter squared. It's just the average, it's the value averaged over the cycle. So most often you'll be using this when doing your Poynting vector calculations.